Welcome back from the break, grade 10s. We're going to dive into metallic bonding. Now this is very, very interesting. So it happens with metal atoms. So metal and metal atoms, it's almost like covalent bonding. They overlap their orbitals. So their outer orbitals overlap. And the most amazing thing happens. We end up having a delocalization of electrons. So what happens is the electrons in the outer orbitals, the valence shell, they hop off and they join all the other electrons that are hopping off the other atoms. And there is what we call a sea of electrons that are constantly moving in between the atoms that are left behind. Now, what's left behind if the atoms are losing, they have delocalized electrons, we are left with a positive kernel, a positive core of these metal atoms. So if you look at the picture here, you'll see that here are the atoms of metal, and there are these electrons, delocalized electrons, that are moving, and they move in between all these atoms. They move in between, and so each one of these core positive leftovers will never be deficient of electrons because there is always an electron around. But it's not necessarily their electron. It's like they're groupies. It's like common electrons that are moving through this metal bonding. So there are things to know, and that is that the outer orbitals are overlapping, that there are delocalized electrons. So the electrons move off of their original atom and become part of the pack. We need to know that what's left behind is the central positive core. So here's the central positive core. I'm going to draw it over here. You can see there, I'm just coloring it in. So that is the central positive core that's left behind. And what happens is a resultant compact crystal lattice of this metal. Now this makes for a very interesting property of a metal, and you will know if you've worked with metal that you can easily bend it, that you can stretch it, so it's ductile and malleable, and it has got conductivity properties. Because these electrons are all available, it can conduct electricity and it can conduct heat, and so it's a very versatile material for us humans. Right, that is our bonding done. I hope you've got a good idea of the difference in the ionic, the covalent, and the metallic bonding. Let's now have a look at some of these questions. So on my screen here, I've got hydrogen can bond with oxygen to form water. We know that, right? So we've got H2O is the formula for water. Oxygen also reacts with magnesium to form magnesium oxide. So magnesium oxide is MgO. How many valence electrons does oxygen have? Okay, so now we need our periodic table for that. And let me just check if I put it in here. There we go. We need this periodic table. Let's have a look at it. We're going to look at oxygen. There, oxygen sits there in the 16th group. And it has got an atomic number of 18. Sorry, not 18, of 8. So we're going to go back and we're going to work with this. I'm going to use the SP notation because that helps me. So I'm going to say 1s2, 2s2, and then we've got the p orbitals, 2p. How many? I can't put 6. I know that 6 is the maximum that the p orbitals can have. I know that I have 8. The atomic number is 8. 8 protons, therefore 8 electrons on neutral oxygen. So I've got 4 already. I can only put 4 there. So what is my valence shell going to look like? It's going to have 4 plus 2, which is 6. And so there are 6 valence electrons. Okay, So 6 valence electrons. If I was asked the valency, okay, so now here it comes up in the next question, valency. Now valency is a very specific term. What that is telling us or asking us is the number of electrons that are shared or given or transferred, let's say, that are involved in a bond. Okay, so not all these 6 electrons are involved in the bonding. The 6 electrons are in the outer energy level. They are the valence electrons because they're in the valence orbital. So how do we know how many electrons are actually involved in the bond? Well, let's go back to our periodic table. I'm going to whiz through there. So if we can see that oxygen is in this group, right? Oxygen wants to be a noble gas. That is its aim. It's stable there. It wants to become the noble gas of neon. And so what is it going to do to be able to become that? Well, can you see that from 8 to 10, the difference is 2. And so that is what the valency of oxygen is going to be. The oxygen will take on 2 electrons, usually, to then get a filled, stable outer orbital. And we say that the number of electrons then involved in a bond, the valency, is going to be 2. Now, you will notice that this word common is here. Now, that's a bit tricky. You might have thought, why common? Because some of these atoms, these elements, can have different valencies with a Y. They can give 1 electron away or take on 1 electron, but their normal state is to take on 2 electrons. So that is why the word common is there. Okay, so valency with a Y is telling us how many electrons are involved in the bonding process. Right, what type of bond is found in water and in magnesium oxide? So now we need to go back to our definitions of what the bonding is about. So water is H2O. We know that hydrogen and oxygen are both non-metals. So what do we know about non-metals bonding with non-metals? We know that it is a covalent bond, and so we can say that the type of bond here in water is going to be covalent. It's a covalent bond. What about magnesium oxide? So magnesium oxide looks like this, MgO. What is magnesium? Well, if we go back to our periodic table, if you've forgotten about it, you'll see that magnesium sits here. Look there. It is in group 2. So we know that this is going to be group 1 is metals besides hydrogen. Group 2, they're metals as well. So what we're dealing with here is, let me go back, is a metal, that's a metal, and a non-metal. Oxygen is a non-metal. So what kind of bonding are we going to have here? Well, we know when a metal bonds with a non-metal, it is called ionic bonding. So that's our answer there. It is ionic. Right, draw a Lewis diagram to represent water, and I think we've done that previously, but let's do it again. So oxygen, hydrogen, hydrogen. How many in oxygen's outer shell? 1, 2, 3, 4. We've just found that out. It was 6. Okay, what about hydrogen? Well, hydrogen has got 1 in its outer shell. It's only got 1. And that's what the Lewis structure is going to look like for water. What about magnesium oxide? This is very interesting now, because this is ionic, right? And it means that electrons are going to be transferred. So magnesium And let's have a look at magnesium on the periodic table. And we see that magnesium is in group 2, and so its valency with a Y is actually going to be 2. It's going to give 2 electrons away. Alternatively, we could use the fact that its atomic number is 12, let's just do that in case. So it's 1s2, 2s2, 2p, 6, 3s, that's 10, 6, 7, 8, 9, 10, so that's 2, okay, 12, so you can see that in its outer energy level, it's got 2 electrons, and those are going to be given away. So we've got 2 electrons here, 2 electrons. What about oxygen, oxide? Okay, 1, 2, 3, 4, 5, 6. I'm just going to change color quickly, and we're back to blue. So what's going to happen? Well, that's going to move into that space. It's given away, remember, that's going to move into that space. What do we end up with? Well, we end up with magnesium, 2 plus, why 2 plus? Because it's given 2 electrons away. And what is the oxygen going to look like? Well, the oxygen is going to have its original, oops, sorry, let's just take that out. Oxygen is going to have its original valence electrons, and now we need to add in the electrons that are accepted, and those will be here, across here, and across here. What is this? It is 2 minus. So that is now the formation of the cation in this situation and the anion in this situation, and there is an electrostatic attraction, and the ionic bond is formed. Right, grade 10s, unfortunately that is all we have time for today. These questions, more of these questions, as you saw, were available. We're going to make them available to you. So go and have a look at them, practice them on your own, and then look up the answers and see if you've got them correct. We hope to see you next time.